Welcome to ONT Lab number 4. In ONT Lab number 4, we're going to configure link fragmentation and interleaving. First in this lab, we're going to identify why do we need a link fragmentation and interleaving mechanism. And we're going to review the 3 different LFI mechanisms that Cisco supports. And we're going to revisit ONT Lab number 2. You might recall how we left things in ONT Lab number 2. We had enabled low latency queuing to improve voice quality, but when we had data traffic, specifically a web page loading simultaneously with a voice stream, even with low latency queuing configured, we had so much serialization delay that the voice quality still was not acceptable. We're going to remind ourselves what that sounded like. Then, after we listen to the voice quality before configuring LFI, we're going to configure a specific LFI mechanism that's appropriate for our topology. We are running PPP, the point-to-point protocol. Therefore, the LFI tool we use is MLP, Multilink PPP. We're going to review the configuration commands to set up Multilink PPP, and we will listen to the voice quality after we have configured this LFI mechanism. But first, let's consider why we might need a link fragmentation and interleaving mechanism to begin with. Let's say that we have a big data frame inside of the router. Let's say that it is a 1500 byte frame, and behind that frame we have a couple of relatively small voice frames. The issue we could have on slow speed links, and by slow speed, I mean specifically less than 768 kilobits per second. It's on those link speeds where we typically use LFI. What could happen in this situation is that it takes so long for that big data frame to get out of the interface that the voice frames are delayed. And this delay is called serialization delay. How long does it take this data frame to be transmitted out of the serial interface? A fix for this is to take the data frame and fragment it, literally break it into different frames, and then, like we're shuffling a deck of cards, we shuffle in the voice frames in amongst the now fragmented data frames. As a result, the voice frames get out of the interface sooner. And let's take a look at the math going on behind the scenes. The formula to calculate a serialization delay is this. We take the frame size and multiply by 8. That turns bytes into bits. Then we divide by the link speed. The units of measure here for link speed are in kilobits per second. In our example, let's say that we have a 1500 byte frame being sent out of a 128 kilobit per second link. That would give us a serialization delay of 93.75 milliseconds. That could start to impact our voice quality to have that much delay before the voice frame ever gets out on the wire. That's why we might need link fragmentation and interleaving. And when I say link fragmentation and interleaving, I'm not talking about one specific quality of service tool. Cisco actually supports 3 different approaches to LFI, and it depends on what we're trying to do. If we're doing voice over IP, and we're doing that over a PPP, a point-to-point protocol link, as we are in this lab, the LFI tool of choice is Multilink PPP. And many people become concerned when they hear Multilink PPP. They may be thinking of how we can use Multilink PPP in an ISDN environment to logically bond bearer channels together into a big logical channel. However, here is some great news. We can do Multilink PPP over a single link. Multilink PPP, by its very nature, does fragmentation. We can tell a single link to fragment large frames going over that interface, and then interleave the tiny voice frames in amongst the data frames that have been fragmented. However, if we happen to be doing voice over IP over frame relay, in other words, we're still doing voice over IP, we are still sending voice traffic to a destination IP address. It just happens to be over a frame relay network. In that instance, the LFI mechanism we'll turn to is FRF12. And sometimes there is some confusion between voice over IP over frame relay and voice over frame relay. It's important to realize that voice over IP over frame relay is sending traffic to a remote IP address. However, voice over frame relay doesn't even involve an IP address. We're simply sending voice frames out of a local DELSI. In other words, a local data link connection identifier, a frame relay permanent virtual circuit. If we truly are doing voice over frame relay, we're not pointing to an IP address. In that instance, we would then use FRF11 Annex C. But let's take a look at the topology we're using in this lab. This lab is revisiting the topology we had back in ONT lab number 2. We have a PPP link between routers R1 and R2, and that link speed is 128 kilobits per second. And the issue we've been having is this. We first, in ONT lab number 2, configured class-based weighted fair queuing to give different amounts of bandwidth to different graphics on a web page. And then we added voice. We placed a voice over IP phone call from extension 2222 over to extension 1111. And while the web page was being loaded with its class-based weighted fair queuing configuration, the data packets as part of that web page completely starved out the voice. We didn't hear any voice. To help remedy that situation, we configured low latency queuing on router R2. And that certainly improved things, but when we pressed a key on extension 2222 and listened to it on extension 1111, it still was not a nice, solid tone. In fact, let's listen to that again. I'm going to place a phone call from 2222 over to 1111. We now have a phone call in progress, and we're going to reload this web page. And while we reload the web page, I'm going to hold down a key on extension 2222, and we're going to listen to the tone coming over extension 1111. And we're listening to this with all of the configurations we gave in ONT lab number 2. So we do have low latency queuing configured. Let's listen. Certainly not the nice, solid tone we were hoping for. And those gaps we heard in the tone, those were not due to dropped packets. Those were due to delayed packets. In other words, we were hearing those gaps because of the serialization delay created by the data frames that make up the web page. Let's turn on our LFI mechanism, specifically Multilink PPP, to see if we can fix this. Let's take a look at the syntax we're going to use. First, we are going to create a virtual interface, a multi-link interface. We specify a multi-link number. This puts us into interface configuration mode for this virtual multi-link interface. Once we're in interface configuration mode, we say PPP multi-link. And like we were saying, by its very nature, multi-link PPP does fragmentation. The challenge, however, is the default serialization delay that it gives us is 30 milliseconds. Cisco's guideline is that we should be around 10 to 15 milliseconds. 30 is going to be too much, so we will want to adjust that. And the way we can adjust that is by using the PPP multilink fragment delay command, followed by a number. And this number is the number of milliseconds of our serialization delay. Typically, we would say PPP multilink fragment delay 10 to give ourselves a 10 millisecond serialization delay. The reason that we would not want to go below that number is we're actually increasing the bandwidth demand when we do this. If we take a frame and fragment it into 10 different frames, instead of having one header, we now have 10 headers. So fragmentation, it does create an extra bandwidth burden on the network, but in a situation like this, where we're dealing with latency-sensitive voice traffic, it's an acceptable trade-off. At this point, our data frame will be fragmented, but we now need to instruct the router to shuffle in the little tiny voice frames in amongst the now fragmented data frames. We do that with the command PPP multilink interleave. And it is this logical multilink interface that the router is going to be using to send and receive traffic on. Therefore, it needs an IP address. We use the regular IP address command to assign an IP address to the multilink interface, and the IP address that we're going to use, interestingly, is the IP address of our serial interface. We are going to rob the IP address from the serial interface and apply it to this multilink interface. And after we have configured this multilink interface, we need to go into interface configuration mode for the serial interface and say no IP address. We're taking away the IP address from the physical interface because we have applied it to the logical interface. And as a final step, we want to tell that serial interface that it is a member of this multilink group. If we had created a multi-link interface with a number of, let's say, 1 as the multi-link group number, we would say in interface configuration mode for the physical interface, PPP multi-link group 1. That's what we're going to do to our serial interface. That's our game plan. Let's go out and configure this on both routers R1 and R2, beginning on router R2. Let's begin our configuration on router R2. First, we create a virtual multi-link interface. We do that with the command interface multi-link, and we give a number. Let's call this interface multi-link 1. Now we are in interface configuration mode, not for a physical interface, but rather for a virtual multi-link interface. We need to enable multi-link on this interface with the command PPP multi-link. And when we do that, by its very nature, multi-link PPP does fragmentation. However, the fragmentation size of the frames is such that the maximum serialization delay is going to be 30 milliseconds. That is above Cisco's guideline for voice, which is 10 to 15 milliseconds. So we want to influence that. Let's say PPP multi-link fragment delay 10, and the unit of measure there is in milliseconds. At this point, we're saying we want to fragment those big data frames, but just a fragmentation by itself is not enough. We want to interleave our little tiny voice frames in amongst the now fragmented data frames. To do that, we can say PPP multi-link interleave. And since this is the interface that we're going to be using to send and receive packets, this virtual interface needs to have an IP address. Let's assign it an IP address with the IP address command, and the IP address we're going to use is the IP address that belongs to interface serial 0/0. Let's say IP address 10.1.1.2, and we give a 30-bit subnet mask 255.255.255.252. Now let's go into interface serial 0/0, and we need to take away its IP address. We can say no IP address, and we say that we want this physical interface to belong to the multi-link group that we numbered 1. Therefore, we say PPP multi-link group 1. At this point, we are done with our configuration on router R2. However, the other side of this link on router R1 also needs to be configured for PPP multi-link. Let's move over to router R1. Sitting on router R1, let's first go into global configuration mode, and just as we did on router R2, let's create out of thin air a virtual multi-link interface. We'll call it interface multi-link 1. And by the way, that number of 1, it did not have to match the other side. In interface configuration mode for interface multi-link 1, let's say PPP multi-link, and like we did on R2, we say PPP multi-link fragment delay 10. We want a 10 millisecond maximum serialization delay. We also want to shuffle those frames up. We can instruct the router to do that with the command PPP multi-link interleave. We also need an IP address for this virtual interface. Let's take the IP address currently assigned to interface serial 0. Let's say IP address 10.1.1.1, again with a 30-bit subnet mask. Let's go into that physical interface serial 0. Take away its IP address with the no IP address command, and say that this physical interface belongs to multi-link group 1. At this point, let's verify that this virtual interface is up. Let's do a show IP interface brief. And interestingly, check this out. Interface multi-link 1 is up. And we also have an indication on screen that our EIGRP neighbor adjacency has been reestablished. Let's test our voice quality. I'm going to place another phone call between extension 2222 and 1111. We heard the phone ring. We now have a call in progress What I'm going to do is reload that web page, and while that web page is reloading, I'm going to hold down a key once again on extension 2222, and we're going to listen to the tone on extension 1111. Let's bring up the web page and do a reload. I'm now going to press down a key on 2222 while we listen to 1111. And at this point, we may be a bit disappointed. If anything, I think the quality now sounds worse than it did when we began. Why is that? This is a question I ask my students in class. I have them think about, why did the quality get worse after we configured Multilink PPP? In fact, you may want to pause this recording right now and think about that. We did correctly configure Multilink PPP. We had already configured low latency queuing. Why did the voice quality deteriorate? So go ahead and pause this recording right now if you want to think about that for a moment. All right, did you figure out why the voice quality went down? Well, you are correct if you said that when we created that virtual multi-link interface, we did not apply the policy map we created back in ONT lab number 2, the policy map called Web. That policy map, it still applied to the physical interface. However, we're using the virtual interface. So here's what we need to do. We need to go back over to router R2 and apply that policy map. On router R2, let's get into global configuration mode and then go into interface multilink 1 and apply the policy map named Web with the command service-policy output web. And when we apply this policy map to the virtual multilink interface, that does not automatically remove the policy map from the physical interface. It's not being used by the physical interface any longer. So as a best practice, you may in the real world want to go back and clean that up. Now, once again, with the phone call already in progress, let's reload the web page and now listen to the voice quality. The web page is now reloading. Let's listen to the voice quality. And that was the quality we were looking for. We didn't solve our quality of service issue with a single quality of service mechanism, realize. We used a couple of different quality of service mechanisms in tandem. We used link fragmentation and interleaving, specifically Multilink PPP, that was our LFI tool. We used that in combination with low latency queuing. Let's now copy our running configuration to our startup configuration and remind ourselves what we have covered in this lab. In ONT lab number 4, we took a look at link fragmentation and interleaving. Specifically, we examined the tool Multilink PPP. We began, however, by reviewing the need for LFI. Why do we need link fragmentation and interleaving? And we saw that we needed LFI on slower speed links. Specifically less than 768 kilobits per second. On these slower speed links, it might take so long for a big data frame to get out of the interface. Our little tiny voice frames are adversely affected because of the extreme serialization delay that they experience. And depending on what we're doing, we may select from 3 different LFI mechanisms. Again, the LFI mechanism that we focused on was using Multilink PPP. We listened to the voice quality before we applied our link fragmentation and interleaving mechanism, and it had issues, so we went ahead and configured Multilink PPP, only to find out that the issue got worse. We then realized that in order for this to improve the voice quality, we had to apply our low latency queuing policy map to the virtual multilink interface as opposed to leaving it applied to the physical serial interface. We then listened to the voice quality again, and it had dramatically improved. We achieved great voice quality while we were simultaneously loading data for the web page. These 2 different applications were coexisting peacefully because we had used a couple of different quality of service mechanisms in tandem.